What if the most important thing about an AI isn't really its size, but its shape? Today, we're diving into a pretty revolutionary idea that lets us see inside the mind of a large language model to actually understand the hidden geometry of its intelligence. This is what we're calling the Eigenspace Revolution.
For the longest time, the whole AI arms race has felt like it's been about one thing: scale, right? More parameters, more data, bigger everything. But what if we've been asking the wrong questions all along? What if a model's real power isn't about its brute force size, but about something far more elegant and efficient?
In this slide, it just lays it all out perfectly. We're shifting from these old questions about how much, how many parameters, how much data, to these much deeper questions of how. Which internal pathways are actually doing the heavy lifting? Which parts of the model hold on to meaning or memory? And maybe most importantly, which parts can we streamline? It's a fundamental change from just measuring mass to really understanding the mechanics inside.
So to answer these deeper questions, we're going to need a new tool. And that tool is what we're calling the Eigenspace lens. This is what lets us finally stop treating the model like some kind of impenetrable black box and start seeing the beautifully complex structure of all the information that's flowing inside it.
Okay, so what in the world is an eigenspace? Let's just push the complicated math aside for a second. The easiest way to think about it is like this. It's the model's internal superhighways. These are the most important, stable pathways where concepts and reasoning and memory flow the most efficiently through the entire network.
And this city analogy just makes the whole thing click, right? Imagine a model's knowledge is a giant, sprawling city. If you want to teach it a new skill, you don't have to rebuild the entire city from the ground up. Nope. You just need to alter a few main roads, maybe change some traffic signs. And that's exactly what efficient fine-tuning methods are hinting at, that small, targeted changes in the right directions can have a huge impact. Okay, so this lens idea is cool, but what does it actually do in practice? Let's apply it to two of the most core mechanics inside every modern LLM: the attention mechanism, which helps it focus, and a super popular fine-tuning method called LoRA. All right, first up, attention heads. Now, you've probably heard of these. They're the little components inside a transformer model that basically decide which words are the most important to pay attention to when it's figuring out what to say next. So the old kind of shallow view was that these heads just look at tokens, almost like a generic blender mixing words together. But when we look through the Eigenspace lens, we see something way more sophisticated. Each head is more like a specialized sensor and a router, actively reading information from specific directions of meaning and then writing that information into others. It's a really targeted communication system.
So the big takeaway here is that efficiency comes from specialization. The most powerful models of the future won't just have more attention heads, they'll have better ones. Heads that act as clean, precise readers and writers for very specific jobs, like tracking grammar, or following a logical argument, or just holding on to key facts.
Okay, next up is something you've definitely run into if you've been fine-tuning models: low-rank adaptation, or LoRA. It's a hugely popular way to efficiently tweak these massive models without having to retrain everything from scratch. And the Eigenspace lens gives us a really fascinating new answer for why it works so incredibly well.
And just like with attention heads, this changes everything. The shallow view of LoRA is that it's just a clever trick, an efficient way to update a matrix. But the Eigenspace view shows us something much deeper is going on. LoRA is actually performing targeted directional steering. It's creating this precise semantic overlay that gently nudges the model's behavior in a very specific direction.
And that is why LoRA is so incredibly efficient. It doesn't have to change the entire model. Because a new skill, like say adopting a specific personality or learning medical jargon, often exists within a really small, compact subspace. LoRA's job is just to find that direction and give the model a gentle push.
All right, now let's take this lens and apply it to a couple of even bigger ideas: how a model learns from another model and how it manages to remember things across those really long conversations.
First up, let's look at this idea of distillation. It's this really cool process where you train a smaller, more efficient student model to perform like a much larger, more powerful teacher model. The basic question is, how do you pass down wisdom?
And this is a huge mindset shift. The shallow view of distillation is that the student is basically just copying the teacher's answers, like cheating on a test. But the eigenspace view shows that for any real learning to happen, the student has to inherit the teacher's internal geometry, the actual scaffolding of subspaces that makes robust reasoning possible in the first place.
You know, this insight is absolutely critical if we want to build really powerful small models. A teacher's real gift isn't just its final answers, it's the internal shape of the reasoning it used to get there. So the best student models are going to be the ones that can inherit a compressed version of that exact same mental geometry.
Okay, now for a question that I know we have all felt. You give a model a massive document, a huge amount of context, but then halfway through the conversation, it seems like it's completely forgotten the first thing you told it. Why on earth does that happen?
Well, the answer lies in this absolutely brilliant analogy. A huge context window is like a giant library. All the information is technically there, somewhere on the shelves, but real useful working memory isn't about the size of the library. It's about keeping the right books open on the desk in front of you. It's about preserving the active directions of the conversation.
So when you think about it, the real future of long context memory isn't just about making the library bigger. It's about building models that can actually protect these durable memory-bearing directions from getting drowned out by the noise of a long conversation. It's about creating stable, directional reservoirs for the important stuff.
So, we've looked at attention, LoRA, memory. Where is all of this heading? Well, it's leading to a really profound change in how we think about what a large language model even is. We're moving away from a focus on just brute force and towards a focus on intelligent, internal organization. You can really see the journey of how we think about these things right here. We started by seeing LLMs as simple token machines. You put tokens in, you get tokens out. Then we got a bit more sophisticated and saw them as semantic state machines, manipulating meaning in this vast space. The next big leap is to see them as subspace machines, where success is all about how well they organize their internal information flows.
And this really gets to the absolute core of the whole idea. The future isn't just about bigger models. It's about better organized models. Intelligence isn't just mass. It's all about structure. It's about building models whose internal subspaces are cleaner, more stable, and more efficient.
And that's the magic, right? When you put on this eigenspace lens, suddenly everything we've talked about just clicks. Attention isn't just attention. It's subspace routing. LoRA isn't a trick. It's directional steering. Distillation is geometric inheritance, and memory becomes this beautiful art of preserving the right internal pathways. It's a single, elegant framework for understanding intelligence. And that is a truly revolutionary way to think about the future of AI.